Hey, what's up, guys? This is Chung here. So today, let's take a look at this hard problem here. Number 1377. Frog position after t seconds. Okay. So you're given like an undirected tree, right? And the nodes are from 1 to n. Okay. And a frog starts jumping from node 1. And in each second, right, the frog jumps from its current node to another unvisited nodes. Okay, if they are like are connected, right, and the frog cannot jump back to a visited node. Basically, if the node is already visited, the frog cannot jump back, which means that the frog we can only go to the unvisited nodes. Okay, and in case if let's say if the frog can jump to different nodes. Let's say from 1, the frog can jump to either 2, 3, and 7, right? And the probability, right, to jump to each node is like it's random. Basically, it's evenly. So the probability to jump from 1 to 2 is one third. Same probability for 3 and 7. They're all one third. Okay. And what else? The So another one is, let's say when the frog cannot jump to any unvisited vertex. Basically, if at the if at the time t, there's no unvisited node the frog can go to. Basically, it will just stay at this node forever. Okay, and the input is like the edges, and then the nodes here, the n nodes. And what it's asking you to get is it gives you the t here. Basically, it means that after t seconds, and also the target. So from 1 to after t seconds to at the target nodes, what's the probability of that? Okay. So I mean, this is like a very it's obviously like a either a tree or a graph problem. I think it's more like a tree problem. Yeah, I think it's tree because it's not like a graph. So, and it asks you to find the probabilities, okay? And for normally, for a tree problem, we usually use like DFS search, right, to traverse to our targets. And a few things we need to be to be careful here, right? Basically, and the first thing is that what's going to be our like ending point, right? What's going to be our base case? So it's kind of obvious, right? Obvious that the base case is when the current node is the target, okay? And then that's our base case. But when the current node is target node, we have two scenarios, okay? So the first scenario is let's see the current let's see the target, for example, with this node here, with this tree structure here. Let's say the target uh, is 3, okay, and the t is let's say 5 in this case. Let's say 5. So what this one means is that at the time 1 here, right? At time 1 here, the probability jump to 2, 3, and 7. They're all one third. Okay, so basically after t1, okay, we're at the target 3 here. But then can we return can we return the one third here? Not. It's probably not. Why is that? Because the problem is asking us to return the probabilities after t seconds. So then I think if we look watch closely here, basically when we're at the target here, we have two scenarios. I mean, the first one is the current time, if the time is equal to the t. Okay, so if that's the case, let's say for example, if the t in this case is 1 instead of 5 is 1, which means when we're at 3 at target, the time it just happened to be our final our like the target time here, then of course we can simply return basically the current probability. That's going to be our answer. Okay, and yeah, and how about another case? Another case is for this one. Let's say the another case. Let's say for example, there's 5 here. When it's 5 here, and if there's any basically if the current time is smaller than t, so this one means that we cannot stop at the target, which means we have to keep jumping. Okay, so in this case, right? So we need to check if we have any unvisited nodes here. So it means that if we have at the target nodes here, if we have any unvisited nodes at this moment, which means in this case we are at 3 here, we cannot stay here because if we have another unvisited nodes, so the frog has to choose one of them and jump to it, which means from 3 it has to jump to 5. So what does this mean? It means that, okay, we were at 3 here, but we couldn't stop at 3 here. It means that we have to jump from 3 to 5. But in this case, since the 3 has already been visited, which means we can never go back to our target, right? Which means the probability is 0, right? It means that we will never be able to jump to here. Uh, and when the time is smaller than t and we have some unvisited nodes here. Yeah, I think that's basically the basic two scenarios, right, of the base case. And other than that, it's just like the DFS search with the calculation of the probabilities. Okay. Yeah, I mean, if you guys can figure out these two like ending scenarios, I mean, I think it shouldn't be that hard to solve this problem. Okay, let's try to code these things here. Basically with DFS, right? I'm gonna create a DFS here. We're gonna have a node here and the time, right? That's gonna be our current time. And I think for my case, I'm passing the current probability to here. I find that this is like a more intuitive to me to understand. Okay, so that's that. And then first, let's create build the graph here, right? So it's gonna be a default dictionary and list. Okay, and then for u and v, right? For u, v, and in edges, okay, graph u dot append v and the graph v dot append u. Okay, so that's the graph, and we're gonna also need like a visited like set. Okay, cool. So that's that. And at the beginning, right, since we always start from 1, that's why we always add 1 here. Okay, and then we'll be having an answer here. Answer equals to 0. Okay, and then we'll be calling this DFS here. So the starting node is 1, and the time is at 0, and the probability is 1 because we're starting from 1 here, right? And then later on we'll be using the current probability to multiply with the different options here. Okay, and then we return the answer. Basically, that's my structure here. And okay, so Now the main part, which is DFS here. So what's going to be our like uh, base case or the ending case, right? Uh, Basically, if the node, right, is equal to the target, okay. When the node is equal to target, I mean, we can certainly uh, verify, right, if we're gonna return like an answer or not. And also it's because this is like once the node has been visited, right, there's no way basically this three, the target node can only be visited once, so that we can simply return from here, because what we know, once we are at the current target here, it's we can basically determine our probabilities already. Okay, it's either like zero or the current probability. Okay, and in order to determine the probabilities here, we also need another like variable, which is the like I said, do we have any unvisited nodes at this moment? Okay, so to do that, I mean with the current node, we have a neighbors, right? So neighbors from the graph, okay, of the node, okay, and to be able to get the unvisited, right? I'm gonna just do a simple process here. Basically, the neighbor for neighbor in neighbors, right? If the neighbor not in visited, okay. Yeah, this is pretty straightforward, right? Basically, since we have a visited nodes here, a visited set here, so whoever is not in the visited nodes is the node is unvisited nodes. Okay, that's why so two scenarios we can return the current probability. The first one is this one, like I said, when the current time is the same as the t, then we can simply return the current probability. Second one is what? Or uh, or the time is smaller than t, right? When we still have some move. Hmm. Well, actually, probably we don't even need this time check here. We can simply use or not unvisited visited, and then the answer will be the probability. So this one means that if the current one is if the time is hmm, if the current time is this and or if we still have some time, do we need to check if the time is smaller than t here? Yeah, what if the time is over, is greater than the t here? Hmm. Okay, let me try to finish this one first, and then probably we can come back to double check if we need to verify if the current time is smaller than t or not. Okay, so now and then we simply return, right? Because we already find the answer, or not, right? Or not means that the answer will stay at zero. So I mean, if the current node is not a target, so what do we know? We need to calculate the current probabilities, right, to the next node, which is going to be the probability equals to what? N divided by the length of the unvisited, right? Uh, oh, I think here we need to do if unvisited. Basically, this check means that if there's any unvisited nodes, otherwise we'll have like divided by zero exception here, right? So that's going to be the current probabilities, and then Okay, so now for each neighbor, right? For each neighbor in unvisited, okay. So here I'm also using like a little bit of backtracking mechanism. Why is that? Because let's say we have a, for example, for this from one, we have three scenarios, 1 to 2 to 3 to 7. So for each of the scenario here, basically every time we have neighbors here, I'm gonna add visited dot add this current neighbor to the unvisited, and then I'm gonna do a DFS to neighbors, right? That's gonna be on time plus one. Also the probabilities time the probabilities. Okay, but that's only for the one scenarios. Since I'm not passing the visited since all of the branches they're all sharing the same visited set here, and after this one for loop, I need to remove that node from the visited here. Remove. Okay, so that I mean when this DFS branch is finished, when we're coming back to the second branch, which is three here, the visited is the is still correct. Okay. Yeah, I think that should be it. Okay, let's try to run the code here. Visited. Okay. 16 unvisited. A lot of typos here. Uh, oh, sorry. So here I think I need to do a non-local here. Answer, right? Because we're setting a global variable here. Yeah, cool. Ah, I see. Yeah, I see. So I think this means that I mean for one of the return conditions here, I mean we cannot simply check if there's no not visited. We have to check, I mean, or time uh it's smaller than the t and not visited. Yeah. So basically this condition means that I mean uh we are at the or you know what actually here. So basically if the time is greater than t, right? We simply return. So then I think we can just do this. I think this should work. Yeah. Yeah, basically I mean I just adding like this one of the branch cut check here, which means that I mean as long whenever the time is greater than t, right? And we haven't seen the node yet, then we know okay, it's obviously like a zero. It's an invalid. Like there's no way we can reach the target, right? Within the time here. That's why we simply do the return here. Otherwise, right? Otherwise we can simply otherwise whenever we have we see the target, we can simply check these two things, right? At this moment, if the time just happen to be our target time here, we can simply set the probabilities, or if the time is not, but there is no unvisited node, which means that even though we have some more time to jump, but since there the frog has nowhere can go, so he has to like keep jumping at the current target until until we reach the time here. That's why we can simply also set this like the probability to the answer here. Cool. Yeah, I think that's pretty much it is for this problem. I mean, it's I don't think it's that hard, but the only things you guys need to be careful is what's the ending point, right? What's the base case, and also the like this is how we basically calculate the current probabilities, and also for each of the DFS, we also need to use a kind of like backtracking to make sure the visited is correct. A current visited for each of the DFS call is correct. And then we pass in the updated probabilities and also the updated node and time. Cool. I think that's pretty much it is for this problem. Yeah, and yeah, thank you so much for watching the videos, guys, and stay tuned. See you guys soon. Bye bye.